Hello, my friends. Um, so we're entering into what is typically a pretty challenging part of this unit. Um, and to be able to handle that, what I want to do is sort of reset the table a little bit, almost a little bit of review, but that'll also allow us to introduce new stuff. Okay, I've been using this analogy. There you go. Using this analogy, between gravity and electricity for a little while now, and it'll work here, I hope, because it allows us to reintroduce some stuff that we're, I hope, pretty comfortable with from gravitational stuff or mechanics stuff, and then apply that, see how that relates at least to electricity stuff. Okay, so big deal. If we're dealing with gravitational stuff, what I call the fundamental entity, it's all about mass. Okay, so here's a big old mass down here. Imagine it being a planet or something like that. And at location X out here to the right, we say that there exists a gravitational field. So if big M there is the only mass in the universe, at location X where there's nothing, there exists some gravitational field there that we refer to as G. Wait, I thought G was gravitational acceleration. Well, they're the same thing. All right, the fact that we say G is 9.8 meters per second squared is due to the fact that the Earth's gravitational field near the surface of the Earth is 9.8, has a strength of 9.8 newtons per kilogram. Okay, now how do we find that strength? Well, like we said, near the surface of the Earth, it has strength 9.8, but anywhere else, what we said is we did something like this. Well, that's one way to find weight. Something's mass times whatever acceleration due to gravity is. That's a gravitational force. Here's the same gravitational force. We can get rid of these little m's, and there's our expression for G, for gravitational field strength anywhere, not just at the surface of the Earth, but at any distance from Earth, or in this case, any distance from mass big M. Okay? Let me try to, I don't know how I can get that back. Well, that'll come back. So what that says now is, there we go. If we have a mass that we put at this location, as long as we're the same distance away from big M, we're okay. A mass here experiences a force that we call Fg. Again, it's mg, or, well, that would be m times g, m over r squared. Well, we recognize that. Fg is g, big M, little m over r squared. Nothing new there, right? Good. Now, now we also said that masses placed in fields have energies, specifically what we called gravitational potential energy, which we wrote before as mgh. Now, h here, let's call it really mgr, because what we really care about is the separation between masses. Okay, yeah, I know h we talked about from the surface of, well, we really said, where do we want to call 0? We can call it anywhere we want. Here we're going to call 0 the center of, say, mass big M. All right, where's little m located? Where is its center located? So we're treating these kind of like point masses. All right, so we can expand this a little. Again, if we use our expression for G, so I'll keep this M. Here's my expression for G, G big M over R squared, and here's that little r. So we say that GPE equals G big M, little m. Well, I get to get rid of one of those factors of r. All right, so there's a different way of expressing gravitational potential energy that we haven't seen before. All right, but using what we've sort of picked out here with an expression for G, our known expression for gravitational potential energy, hopefully that works out for you. All right, now here's where it gets a little bit tricky. We introduce this whole new quantity, all right, because, oh boy, let me move this a little bit. I'm just going to rewrite as GPE equals G big M little m over R. Okay, now what if we put different masses at that same separation from big M? All right, well, they all have different values of gravitational potential energy, right? Because our values of M here are all different. But, our biggest M here has a big potential energy. Our medium size M has a medium potential energy. Our small m has a small potential energy. But if we divide the gravitational potential energy of this one by its big mass, we get a certain quantity. If we divide the medium gravitational potential energy of this one by its medium mass, we get the same quantity. If we divide the little gravitational potential energy that that one has by its little mass, we get, again, the same quantity. And what I'm saying is, if we do this, GPE per unit mass, we get the same value everywhere. Everywhere on this line, I'm drawing a green dot, everywhere on this line, an equal distance away from mass big M, there's an equal value of what we call potential energy per unit mass. Okay? And that's called gravitational potential. All right? It's not potential energy because we would write it as, well, GPE, here's GPE, divided by the little m. So all we're left with is GM over R. All right, now notice I don't even write a variable for this because A, we don't really use it in AP, and B, I don't really know what the standard accepted variable is. Notice it looks kind of like all of them, right? It looks kind of like gravitational field strength, except R isn't squared. It looks kind of like gravitational potential energy, except there's only one mass. So that's what makes these things tricky. The equations all start to look like each other. All right, but notice, gravitational potential energy depends on the size of the mass, the magnitude of the mass that makes a field, and how far away from that mass you are. All right, so at location X, right here, there is some gravitational potential. You put a mass there, now that mass has gravitational potential energy. All right? Now, if that's a lot to wrap your head around, I certainly understand. What we have to do now is sort of draw all these analogies, these same analogies, but for things with electricity. All right? So, for sure, we start with the top. The fundamental entity, the thing we deal with here, instead of mass, is charge. All right, so down here we have a big charge Q that makes a field. So at our location X here, we say that there exists an electric field that we call capital E of strength. Hopefully we're okay with this now. A couple ways to do it. But I'm going to write it as this, K times big Q over R squared. All right, if we go back a page, notice we have gravitational field strength is G, the constant, times big mass over R squared. Here, we have electric field is K, the constant, times big Q over R squared. So, very similar equations. Now, so anywhere on this line, this dotted line, there's an electric field of the same strength. Okay? We put a charge there. That charge experiences a force, an electrostatic force, that we can say is Q times E, or Q times K big Q over R squared. Or, oh yeah, we recognize this as Coulomb's law. K doesn't matter the order of those Q's. Product of the Q's divided by the square of the separation. Right. So again, you go back a page that looks just like universal gravitation, well, at least in structure. But here we use charge instead of mass. Here we use K instead of Q. Sorry, K instead of G. All right. Now, Just like a mass has potential energy, what we call gravitational potential energy, a charge has electric potential energy. We call that, or AP at least, calls it U. All right, I think your book calls it EPE, but we're going to call it U here. All right, now let's think back to the last slide. Gravitational potential energy is mgh. All right, I'm just going to even write that, mgh. Well, what's our analogy for M? Well, here we use charge instead of mass. Which mass or which charge? Well, the one that we place in the field. This charge has potential energy. All right, here's G. Well, that's gravitational field, so we'll use electric field instead. And then H, we really said, well, let's treat them like point masses, and let's make that the separation between them. So we keep that here, QER. You'll see it as QED sometimes, okay? Now we can rewrite that as Q times E is K big Q over R squared, again, times R. We get to get rid of one of these, and we end up with U, K, little q, big Q over R. All right, look back to the slide before, you'll see it's the exact same structure of an equation, format of an equation that we have for gravitational potential energy. Instead of G, we use K. Instead of masses, we talk about charges. Now, same thing we did before. You know, all these different charges have different potential energies, right? Because the Q's are all different. But anywhere at that same distance from charge big Q, there's an equal value of what we call potential energy per unit charge, right? Take this one's relatively big potential energy because of its big charge, divide by that big charge, and we get a certain quantity, right? Divide this one's medium-sized potential energy by the fact that it has a medium charge, we get a certain quantity. Divide this one's this little electric potential energy by its little charge, we end up with this same quantity, which is electric potential energy divided by that charge. All right, so that's K Q big Q over R divided by Q. Well, here's divided by Q. Well, we get rid of the Q. And we have this electric potential, which we actually call capital V. Potential energy per unit charge. And we can write it like this, K Q over R. All right, so here, for electric potential energy, yeah, we actually use capital V. All right, now a couple of questions a couple things we haven't nailed down. Units for all these we should be sure of. E measured in newtons per coulomb. All right, force for sure measured in newtons. Potential energy, hopefully we're okay here, measured in joules. So that leads us to what is potential measured in? Well, I like to look at it here and here. Potential energy is joules. Charge is coulombs. So potential measured in joules per coulomb, energy per charge. This is one of the hardest concepts for people to wrap their heads around, just because it's such an abstract sort of thing. All right, again, we're saying at this location right here, there's a certain value of electric potential. All right, at this location here, there's a different value of electric potential. All right, at this location, there's a different value. And based on the value of that potential, whatever charge you put there has some potential energy. So sometimes I even call electric potential, I say it's like potential energy, the energy that something would have if you were to place it there. Okay? So that's tricky. Let's see if we can do a couple of examples to show how this stuff works. Okay, one of the biggest things, one of the most important things about, or differences at least, between electric field and electric potential, is this. And I haven't been as good about this as I should. Electric field is a vector. Right? That's why we've been able to draw electric fields, right? We can represent electric field with arrows representing how strong it is and what direction it points. One of the nice things actually about potential is it's a scalar. All right, so there's never any, components or Pythagoreating or anything like that, and that can actually make potential easier to deal with sometimes than electric field. So what we're going to do is we're going to figure out the electric field, the net field at location X, and the net potential at location X. So first for field, here what we can do for sure is, we'll draw it. So I'm going to turn this one into a blue one so I can say, okay, at location X, there's a field from charge 1 that I'll call E1 that points away because it's a positive charge. Fields point away from positive charges. Okay? And there's a field from charge 2 that looks like this. I'll call that E2. It points downward because fields point toward negative charge. Okay, now I'd have to define probably, let's call this R1, and let's call this R2. So if we wanted to find the net electric field that I'll draw like this, here's E net. We would say that E net is, well, the square root of E1 squared plus E2 squared. Right? Because those two electric field vectors are at right angles, if we want to find their resultant, we Pythagorate. Okay? And if you want, we can turn this into, let's see, KQ1 over R1 squared. Don't forget to square that stuff. Plus KQ2 over R2 squared. Don't forget to square that stuff. Right? These squareds here are because we're squaring that. Okay, so, if we knew Q1, Q2, R1, R2, we could find the magnitude of the net field. All right, we could also do some trig to find whatever angle, if we wanted to find that angle, we could do that. All right, so hopefully nothing too new there. Now I want to show you how to do scalar stuff, or sorry, how to do potential stuff. And again, it's a scalar, so you literally just add them up. I'm going to say it's V1 plus V2. Okay? Nothing to do with direction. There aren't directions. So all we literally do is say, well, this is KQ1 over R1 plus KQ2 over R2. Now, if you remember before, we said here, for electric fields and forces, we never use sign of charge. Well, that's because electric field's a vector, and the sign of the charge dictates how we draw the vectors. Since potential is a scalar, we have to use the sign of the charge. It seems strange, maybe it does to me, I guess, but here we always use sign. So this is actually going to turn into, well, I have to do this. I really have to make it minus here. Well, you know what? Let's go back to here. Let's say that it would really turn into like this, that V total, V net would be K Q1 over R1 plus K times negative Q2 over R2, right? Q2 is a negative charge. So that's why we said this really is the same thing as K Q1 over R1 minus K Q2 over R2. Hopefully one of those ways, hopefully you get why those are the same thing. Okay, so we actually use the negative charge there. And that's it. There's no, like I said, there's no Pythagoreating. You just add them up. Fair enough? All right, so let's make it a little trickier. Oh yeah, so let's go to this idea of potential difference. All right, let me just pop ahead one more. Yeah, okay. So here's this idea of potential difference. All right, and the idea there really is that, if we go back a couple of slides, like we said here, right? There's a certain potential here. There's a certain potential there, a certain potential there, and those potentials are different, right? Because we're a different distance from the charge Q that makes this field. All right, so, from here to here, we say there's a difference in potential, and that's what we refer to as potential difference. All right, now that has another name, and it's called voltage, which is something that that a lot of you have, a word that you've heard. Now we get to talk about what that means. So, potential difference, literally the difference in electric potential between 2 points in a field. Now, electric potential is V is electric potential energy per unit charge. That means potential difference is, well, we can write it sometimes as delta V, but sometimes they just write it as V. You got to be careful of that. Well, it's got to be delta U per unit charge. Now, delta U, change in potential energy. What do you have to do to change something's potential energy, right? What do I have to do to take a mass and give it more potential energy? Well, I've got to push it through some distance, change its height. I have to do work. So you might remember that this is the same thing as work. Delta U is the same thing as work. How do you change something's energy? You do work on it. All right, so here's a big one. Okay, and it tells you, what voltage really is. Voltage is the amount of work that can be done per unit charge, or the amount of energy conversion that can be accomplished per unit charge. All right, so we're going to apply that. There's a very common kind of question that will apply to situations like this. All right, so again, this is kind of like a review here, but here we start to find all sorts of different, really all these different quantities, and we want to make sure that we can, really understand what the question's asking and that we know the right approach. All right, so simple one here, just with a point charge, that's a positive charge. We want to find the electric field. All right, so electric field, E is KQ over R squared. Now, how do I know to use KQ over R squared and not FE divided by Q? Well, because I know what the charge is that makes the field, and I know how far away I am from it. And even though this is a lowercase q is a given, that doesn't necessarily mean I use F divided by Q, right? You notice I don't know any force in this question. I know a charge that makes the field. I know how far away we are from it. So forgive me, well, let's see, 9 times 10 to the 9th times 5 times 10 to the negative 6th divided by 0.025 squared. I get 7.2 times 10 to the 7th newtons per coulomb. Nothing bad there, right? Good. Now, potential. Well, that's V, and we do that as KQ over R. All right? So that's going to be, well, 9 times 10 to the 9th times 5 times 10 to the negative 6th divided by just 0.025. 1.8 times 10 to the 6th. And again, what's our units for potential? That's joules per coulomb. Okay? Okay. Now, potential energy of a proton at X. So now we're talking about actually placing a charge at location X. 2 ways to do potential energy, right? One, we said that it's K, little q, big Q over R. All right? And nothing wrong with plugging all those things in. You'll certainly get the right answer. But remember, we also said that there's a definition for what potential is. Potential is potential energy per unit charge. So that means that potential energy is Q times V. So all I have to do really is take my electric potential that I found here and multiply by the charge of the thing we put in that field. Well, in this example, that's a proton. So I'm going to do that 1.8 times 10 to the 6th and multiply by the charge of a proton. Same as the charge of an electron, just positive. And I get that U is 2.9 all around times 10 to the negative 13 joules. Fair enough? Okay, now here's the real common question, the most common and probably the trickiest for a lot of people. How much work do you have to do to bring a proton from location X to a different point that's 5 centimeters away, right? So we're talking about bringing the proton from here, where there's one potential, to over here, where there's a different potential. Or we're talking about moving the charge through a potential difference. Well, we know that there's a relationship between work done and potential difference. And we say that, that delta V, potential difference, by definition, is the work done per unit charge. Okay? Or we can say that the work done is Q times delta V. Or we can say that it's Q times V final minus V initial. V for potential, of course, not velocity or anything like that. All right? Or Q times, well, I need the potential at 5 centimeters away. That's going to be, well, I'll do KQ over R5 minus KQ over R 2.5. Now, if you're careful here, and again, you have to actually calculate the potential here at the location 5 centimeters away. We have the potential at the location 2.5 centimeters away. I get an answer of negative 1.4 times 10 to the negative 13 joules. All right, let's talk a little bit about this sign. Why is it negative? All right, again, how much work is done to bring the proton there? It says that there's a negative amount of work done. All right, and here's the deal. To bring a proton from here to here, well, remember, this is a positive charge already. So that positive charge here will push this proton by itself. Right? It will push it from a location here to a location here. You don't have to do anything. In fact, the only thing you have to do is probably push back this way to keep it from going any farther. All right, so when we say how much work do you have to do, you have to push this way while the charge moves that way. Hence, the amount of work done comes out as negative. All right, if the question was how much work is done by the field, well, we'd say that amount of work is positive because the field pushes to the right while the thing moves to the right. All right, yeah, I just noticed that we skipped this one. And this one's actually easier, but the nice thing is we can do the same exact thing as we did here. All right, I'm going to go from this step and bring that right to here. That work is Q delta V. V final minus V initial. Now, how much work is done to bring a proton from infinitely far away? From infinitely far away. Well, infinitely far away, that means that's our initial place. Here's an expression for potential. If R is infinity, what's potential? Well, if the bottom here is infinitely large, the potential is 0. All right, so that means it starts at a location where potential is 0. And all we have to do is do Q times V final, or our V final is really this. All right, and notice we've actually already done that right here. So our answer for work is positive 2.9 times 10 to the negative 13 joules. Why is this answer positive? Well, if we have a proton really far away and we want to move it to this point right here, we have to push it the whole time we're trying to move it in the direction that it moves. Right? We push it from all the way out here. We have to push, 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 push till it gets here. And why do we have to push? Because the field is trying to push it back this way. All right, so that's why this answer is positive. Really tricky thing about signs with these questions. All right, when are they positive? When are they negative? That's the way I always think about it. What would the field want to do, and do I have to, push against what the field's trying to do, or do I have to actually hold it back from making the field move it any farther? Okay. Here's a whole bunch of information. There's some trickier problems that we're going to go through in class with multiple charge stuff. I think this is a good place to stop for today. Go back through, make sure you can tell where all this stuff came from. Like I said, a lot of information and some tricky stuff, and we'll work more on it on Monday. Thanks, guys.